They're on this YouTube. I have like a YouTube page from that one year. There's I mean, I would not recommend the videos. Like and subscribe. Yeah. Don't forget to like and subscribe. Okay, so we're gonna do this. Yes. Let's see if I'm not sure if this will be easy to see. It's a ramp. Good morning, Mr. Thompson.
Good morning, can I see Jagger?
Can do some roly polies.
Just of all little warning, the girls' basketball team made the stage, and everyone we're gonna have again.
Yay! Is that next week?
Yes.
Okay. Oh, the pep band and all that stuff.
Yeah.
Okay. Okay. So here's the question, and it's kind of well, it's not surprising, but it's interesting how if you ask someone, let's forget these for a second. If you ask someone like, "Hey, I'm gonna roll these down a ramp." Oh, I got this. This is like kind of a heavy like steel ball, and there's just like a wooden cylinder. And you said, who would win the race if these rolled down the ramp?
Cylinder.
You think the cylinder? What do you think people always?
The steel ball.
Well, people always want to know which one's heavier. Yeah, as we're going to see, spoiler alert, we're going to find that the mass of the object itself does not really matter. It's like the famous, well, here's one. Right? If you drop them, they fall at the same rate. We've seen with the mass sliding down a frictionless surface, the mass doesn't matter for that either. And we're going to see that for rolling, the mass won't matter again. But what do you think does matter?
I mean, density.
Density would, yeah. Well, everything we're going to think about is going to have uniform density over where its mass is. But that certainly would matter. If you had like a ball, and like the core of the ball was denser than like the outside of the ball. Take the Earth for example, and that would certainly affect like how it would roll. What's going to matter is the mass distribution. So a solid ball has a different distribution of mass than a cylinder, and especially this. I'm pretty sure this is hollow. I actually don't know what's inside this, but I think we're going to roll it and see what happens. So anyway, let's do this demonstration. This is actually a specialty item. These have the exact same mass. One's made of some kind of like wooden substance. I think what is it called when they like pulverize? Yeah, they pulverize the wood and then like reconstitute it.
They like get a bunch of wood shavings and wood chips glued together, press it and press it and press it and press it.
Yeah.
Like heat and steam and stuff like that. That's how they make it.
Yeah, I think this might be something like that.
It looks like MDF. That's just pulp or clear coat on it.
Yeah. Anyway, and then this is just like a steel ring. Okay. So the question is, I really want to make sure it doesn't. I think this should hold. Well, maybe I'll do this. Okay. Taking bets. Who is going to win the race?
The wood. I got 30 on steel.
Why the wooden one?
Because it's which is great.
Yeah, that's what I meant.
Right.
30 on wood.
So for a solid cylinder, right, it's I is 1/2 mr squared.
Yeah.
For a hollow ring, it's going to be 1 times what? Just mr squared. So this is going to have a smaller I value and thus is easier to rotate. Here's another physics question for you. If you had to identify why does something roll? Friction is key. Yeah. You know, we're going to talk about this in more detail in a second. But when something's on here, yeah, why doesn't it just do this? Right? Why does it? What causes it to start rotating?
Friction from the object.
Yeah. So the friction, there's friction happening between the surface and the object, and that exerts a torque on the round object. So you can think of some. So that's one of the things that I think makes physics interesting is you can take these really simple things you've seen a million times, like a rolling object, and you can describe it.
Like your tires sliding across the ice, and like when you try to step on the gas and your tires just spin out. There's not enough friction for the sort to turn the wheel.
Yeah, exactly. And like with bowling, you ever go bowling? You know, Hunter, you're a good bowler, right? Decent bowler, right?
I'm all right.
When you roll that ball, a lot of times, yeah, it doesn't quite roll, you know, because it's a low friction environment. Anyway, it's okay. Let's see who wins. Ready, go. I knew that was gonna happen. Oh, I'll clean that up later. Why don't I just get something heavier? I should have gotten textbooks. Anyway, you saw the one, right?
Yeah.
Right, yeah. Good stuff.
Chair.
Yeah.
Oh, it didn't spill that bad.
You can clean it up.
It's a little. Man, if you got one of those brooms that Geyser was handing out this morning, then so much. Yeah, apparently you sent out like a teacher email. It's like, I've got brooms. You want some? I don't know what it actually said, but that's what I'd like to imagine it said.
Yeah.
Okay. Broom time.
And
Yeah.
Ozzy was like, "Hey, I want a broom," and Geyser said, "Well, if you responded to my email."
Oh. Okay, so we all saw what happened, right? Who won?
So,
The wood. Okay. So once again, just to show it again, here, this is in front so you can see better. We'll do a couple races here. Then we're gonna do I think a fun derivation. Okay. So the wooden. I should just emphasize the solid cylinder beats the hollow cylinder. Smaller I value, lift takers. How about this? What's up?
how do you identify, I guess, if it's like hollow? Because what if you like increase the thickness of like the outside? Would that still be hollow or like something else?
Yeah, so that's a good question. So like this, yeah, technically this is not. It's not a perfect ring, but this is thin enough that
It's pretty much like just one eye.
So
it one R value.
Yeah.
Yeah, pretty. Let's like say close enough. But there is. I mean, I could go on Wikipedia right now and find the formula for like this, where you have like an outer radius of say A and an inner radius of say B, and the formula. I think it's called like an annulus or something. Someone has derived the formula for that, and in fact, it might just. I'm guessing it actually might just be because it's basically you take a solid cylinder, a solid disc, which is 1/2 m/r squared, and then you just subtract away the contribution from the inside one. Although, I don't know, hold on, part of me's thinking, am I making that overly easy? That actually might be correct, because yeah, you basically say, start off with a solid cylinder and then just subtract away, the contribution of the smaller cylinder. I think that might be correct. But you actually have one of the items we can race is someone made this years ago. I think it's in here. Unless it got thrown away. Oh, it's here, yes. Well, I've got where's the other? Oh, this one might have broke. I had one of these that There's some MDF for you.
Yeah.
But look at this. So someone made this. They took it in the shop because, well, who would think would win? This thing's heavy. This is like, I'm pretty sure this is solid like steel or something. Huh? Mass doesn't matter. There is a hole drilled through it. So that's kind of what you're talking about, right? It's like a really thick. So who should win between this and this? Should be this, because he's closer to a solid cylinder than he is, right? So this is probably.
Do you want me to hold them?
Yeah, can you just hold that? And just let's see who wins this one. But what will be interesting is to race this against some other objects. So as you can see, this guy did win. However, quick little review of our formulas here. What's the I value for a solid sphere?
2/5.
2/5 mr squared. While we're at it, the I value for a hollow sphere is 2/3 mr squared. So who should win? This is a solid ball here. This is much heavier, but who should win between the solid sphere and the something in between a hollow cylinder and a solid cylinder? Still think it's cylinder. Well, would you agree that because the hollow cylinder is mr squared and the solid cylinder is 1/2 mr squared, that if you were in between that, maybe you're 0.75 mr squared or something, right? Maybe you're 3/4 mr squared. Certainly the solid sphere should always be less than that, right?
Yeah.
Does that make sense?
Yeah.
Because the solid sphere should already be able to beat the solid cylinder. Let's show that real quick. Okay, I got a solid sphere versus a solid cylinder. Let's see who wins. Oh. Spheres can be a little troublesome. It's close. It was pretty close, but the sphere won by a little bit. Notice how 2/5 is awfully close to 1/2, 0.5 versus 0.4. So it's gonna be a pretty close race. Whereas like 2/5 is much less than that. So if we do a hollow, let's do. I've actually got some hollow cylinders. Here's one from. It's like a little tube you get at the hardware store. This should be a pretty big difference. Got pwned right there. I've had a whole bunch of roly-polies in here actually.
What happens if you put the ball in the cylinder?
Good question. So your I value would be a combination of those. What makes it tricky though is you know what I realized? You saying that made me realize this. We were talking about that annulus earlier, that kind of like this shape. I think I was oversimplifying the calculation a bit because the m in there, when you say 1/2 mr squared, what m are you talking about? Well, like when I say this guy's I value is 1/2 mr squared, m is the mass of the thing. So if you drill a hole through it, well, you're changing the mass. So it does get so when if I put this inside this or something, I would have the 1/2 mr. I'd have the mr squared from this guy, plus the 2/5 mr squared from this guy, but a different m. His mass is different than his mass, so it's not super simple always to do that. But anyway, I got some more roly-polies. Should be a good one. How about here's a hollow cylinder versus we've already established that a solid sphere is king, right? Like we can just do this one real quick. This should be a very clear win for the sphere. Like not even close. Or how about this? Solid sphere against what I think is a hollow sphere. I'm pretty sure. Well, it kind of sounds hollow. Well, I just mean I can't know for. I mean, I guess I could put it in. I wonder if it floats. You think this could float? Maybe. Let's race them. Race time. Okay, ready? Who will win? Solid sphere. So, what?
Solid sphere's king.
Yeah. So anyway, I guess one last thing I want to show you is people will always be like, well, isn't it just a heavier object? Hopefully we're already established. Heavy, it doesn't matter if it's heavier. So here's a really heavy solid cylinder. Very heavy solid. Okay, this one. So who should win? This small, not very heavy solid. This is the solid one. Solid sphere or solid cylinder. So even though the solid cylinder is way heavier, it was close. The ball was a little bit ahead. Again, why is it so close? Well, those are pretty close eye values. Hello, Hunter. And there's another factor here because this is not a perfectly smooth surface. Like if you're a bit heavier, you can kind of like power through like any little bumps. Whereas a lighter object is maybe more affected by them. Although, even with that being said, you still like, I don't know, here's a solid, or here's a hollow cylinder. Little guy, little hollow cylinder. Big hollow cylinder, much heavier. Let's race these guys. It should be pretty close. But hopefully we can, if there is a difference, we can explain the difference with maybe, I don't know, something. I feel like this guy won by like a centimeter. Let's try it again. But maybe you can explain that with, well, this guy's so little and light that any little like bumps or perturbations from its path are going to have a greater effect on it. I don't know, pretty close. Pretty close. But yeah, like idealistically, perfect physics world, spherical cows and such, they should be the same, which they were pretty close. But yeah, like it's like why you want bigger wheels on like an all-terrain vehicle because getting over bumps and stuff. Kind of similar kind of principle. But. Okay, so anyway, let's move on. We're gonna do the derivation for it's like the last problem. Okay. How's it going, Hunter?
Not too bad.
Not too bad. So the problem is, correct me if I'm wrong. It is the very last one, right? That says we're going to basically derive. Yeah, we're going to derive a big formula. So we're in this space here. It's not going to be like a super massive amount of math, but enough to take up a quarter of a page. And oh my goodness. So just read that prompt real quick. Okay, so everyone understand what we're talking about in this question?
Yeah.
So here, this will check to see if you understand. What is K for a hollow sphere?
Oh.
Don't overthink it. It's a really easy question, actually, huh? No.
1/2.
2/3.
Oh, hollow sphere.
So-
I was reading stuff.
So so the first thing that we're going to do is say, well, instead of deriving this formula for every different object, what if we just say, well, most objects can be described by I equals some constant times m times r squared, right? Well, so you see how in the formulas, right? Like, what's the k value for a solid cylinder? 1/2. What's the k value for a hollow cylinder? 1. We get the idea, right? For a solid sphere, it's 2/5. For a hollow sphere, it's 2/3. So now it's likely, if you guys remember that wiki page I showed you that had the big list of all the crazy ones, like, you know, you could have like a tetrahedron and describe that in terms of something times mr squared. Now, not that a tetrahedron would roll down a ramp. This would only work for things that can roll. But I guess what I'm saying is, like you were talking about earlier, Jager, like what if you had an object like a ball that had varying density? Say the core was heavy and the outside was light. Well, it's likely that for an object like that, if it's spherically symmetrical, you'll be able to just derive like some kind of formula, and then oh great, we'll be able to use the formula we derive here to describe its role in motion. So let's get into it here. So this is a round object, radius r. There's going to be two vectors that I really am focused on. One of them is just how much does gravity tend to pull this thing down the ramp? Does anyone remember like if we drew the gravity vector mg and then found the component that points down the ramp?
mg cosine theta.
Very close. It would be mg sine of theta. Remember, as theta gets bigger, this gets bigger. Okay? Then there's another force that's really important here. We touched on it earlier. What's going to cause this thing to roll? Friction. So right at this point, this contact point, there's going to be a friction vector. So this is called the force of friction. Are we okay with that? And so we're going to do Newton's second law now. We're going to say, well, if there's a force trying to push it down the ramp, and there's a force kind of opposing it, it's an interesting force because it does slow down the process. Like a frictionless block will slide down and beat anything rolling because there's nothing holding it back. It kind of does two things. It kind of slows down the process of it getting down the ramp, but it also causes it to rotate. So it's a little bit, there's going to be some substitution there. So anyway, Newton's law, right? It's going to be this, like F net equals MA. F net equals MA. So F net would be this, mg sine theta, minus whatever this friction force is, which is equal to the mass times the acceleration. Any questions yet? Now, usually at this point, someone goes, isn't there like a simple formula for friction force? And the answer is, well, sometimes if I've got a thing sliding across a surface, or if I've got a thing in a static state, but, you know, like for example, this, if I just, very easy here to say, well, okay, the friction force is, you know, mu times mg cosine theta, and it has to be equal to the mg sine of theta. You can set them equal. Or even if it's sliding, but this is different because it's actually, if you think about it, it's static friction happening there, right? it's like when you're driving your car. Do you want there to be static friction between your wheels and your tires in the road, or kinetic friction? No, you want static.
No.
Because if it's kinetic, that means you're sliding. You don't want to be sliding, right? So if your wheel, right, if this is your wheel, your tire, whatever, and it's skirt and it's actually rubbing against the road, that's bad. That means you're, huh? Maybe you're doing a lit burnout. Yeah, you're Tokyo drifting. But generally speaking, you want, if you think about it, if you zoom in on the point of contact between the tire and the road, they're not rubbing against each other. It's not kinetic friction. It's actually a static, but the point of contact is moving. So it's a bit more complicated is all I'm saying. So anyway, so what you are going to do is say, well, I'm going to try to do some, I'm going to try to get to that. So the first thing you might do is say, well, isn't it the case that the torque on the roly-poly is equal to that force times the radius? That's the first thing we might say is true, right? Torque equals Fr. And then say, well, isn't it also true that torque equals I alpha?
Oh, yeah.
And isn't it also true that for a rolling object, acceleration equals alpha times r?
Yeah.
Would you agree that all three of those equations must be at play here?
Yes.
It's a rolling object. What up?
Can't we just like not do F net MA if we're just trying to find acceleration, and then just use the A equals alpha?
We're getting there, yeah, because eventually we're trying to solve for A here, the acceleration. Because remember, for a frictionless block, the answer, do you guys remember the answer to the question of, if this was, instead of being a roly-poly, this was like a block sliding down a frictionless ramp, what's the acceleration?
The MGG. Data.
Close. You would set that equal to MA, right? Because that would be the net force. You'd set that equal to MA and just get d sine theta. Remember that one?
Oh,
So we don't know what A is yet. So anyway, here's a substitution. So we're going to go, okay, well, while we're at it, I want my I, so there's a bunch of substitutions that we're going to have to be clever about here, right? So I want to get this involved too. I want my final formula to involve K, right? Because I hope that demonstration pointed out that the K value is really what determines how quickly it's going to roll down the ramp, as well as how steep the ramp is, of course. Does that make sense? So I need to get this guy involved. So let's go ahead and replace this I with K M R squared. Yeah. That makes sense?
Yeah.
And then let's replace this alpha. What do you think I'm going to replace the alpha with?
Acceleration of the radius.
Very good. Y'all see that? Makes sense? Yes, no, maybe so.
Yeah.
So torque then is K M R times A. It's a little, it almost like says a word. Kimura.
True.
And then let's put that in there. So K M R A equals F R. Then what happens?
R's cancel.
The R's cancel out and you get F equals K M A. That's nifty. And that is what's going to go in there. It feels me? So now we get mg sine theta minus KMA equals MA.
Can the MAs be in the
Well, look, all these terms have m, the mass of the roly-poly. So that means I can divide both sides by m, and they all cancel out. We're super close.
And then you get G times beta minus K A.
If it's okay with you, I will just add this over right now.
Yeah.
So the right side is going to be a plus ka. Right?
Yeah.
And so g sine theta equals a times 1 plus k, like that. And we get our formula. That makes sense, the last step. So for a frictionless block, for going back in time, frictionless block, what's the K value for a frictionless block?
G sine. No.
It's a kind of a trick question. Does the block roll?
Zero.
Yeah, the block doesn't roll. You don't need to consider its rotational.
Right.
I mean, there is an I value for a cube. You can derive it. It's on that Wikipedia list. But for something that doesn't need to roll, you just say, well, we don't need to think about the K value. So the I value. So the K would be 0. But do you see what would happen if K was 0?
Yeah.
You would just get G sine theta, the old result. So what happens if K is 1?
Half of G sine.
You get half of G sine theta. What object has a K value of 1?
The hollow cylinder.
The hollow cylinder. Very good. Then there's some of them get a little bit more complicated. Now watch how easy this is going to be, because now do I have to do this whole mess for those 4 different objects? No, because now I just go there. I hope you had enough room in here to derive it. You just go back up here and go, well, for a solid cylinder, I'll leave this as an exercise for you guys. We'll check our answers to make sure no one got it wrong. But
So what, you just plug in 1/2 for the K.
exactly.
And
So
then find A.
yeah. So the acceleration then for question A says, well, what about a solid cylinder? Well, for a solid cylinder, K is 1/2. So I get an acceleration of
Or G sine theta over
1 plus 1/2. Well, 1 plus 1/2 is 3/2, right? And dividing by 3/2 is the same as timesing by 2/3. So now you can conclude that, hey, for a solid cylinder, its acceleration as it rolls down the ramp is going to be 2/3 as big as that of a frictionless block. Okay. And then so on and so forth for all the other ones. So. And then the last thing I want to discuss with you here. Well, you guys go ahead and finish those. Fill in A, B, C, and D. Let's check our answer. What do we get for B?
1/2 G sine theta.
1/2 G sine theta. How about C?
Oh, I just have to put it at 1/2 or keep it G sine theta.
Either one.
Would it be 5 seconds?
Yes. Do y'all get 5/7 G sine theta?
Yeah.
Then how about the hollow sphere?
I didn't do that one.
Okay, just go ahead and do that. The bottom's going to have 1 plus 2/3, which is 5/3. So your final answer is 3/5 g sine theta. All right, makes sense?
Yeah.
All right, you'll see if you look at those coefficients you end up with, they rank out the same way that we already ranked them out, right? So the fastest, who's the fastest? The solid sphere with the factor of, it was 7/10, right?
Yeah.
7/10 is the biggest out of all those. Yeah. So the coefficients we found were 7/10, 2/3, 1/2, and yeah. Also, it shows you why the solid sphere was so close to the solid cylinder, right? Because 0.6666, right, is awfully close to 0.7.
Yeah.
The 7/10, right? They're very, very close to each other. So the solid sphere only has like a slight edge in that race. Okay, last question. Albert is going to roll 2 solid cylinders down a ramp. One of them has a 10 centimeter radius, and one has a 20 centimeter radius. It's not the exact same values, but it's kind of like this. 2 solid cylinders, one big, one small. Who will have the greatest linear acceleration? They're going to be samesies, right? See how R is not in this?
Yeah.
So you'd agree that this and this will have the same linear acceleration. I mean, we've already raced them. Like if we rolled them next to each other, they'd roll with the same acceleration. However, who would have the bigger angular acceleration? Mm-mm.
No, I did that.
Would be the little guy. You see how look, well, just intuitively, look, the big guy, to cover this distance, doesn't have to roll, doesn't have to spin that many times. For this guy to cover the same distance, he has to spin a lot of times. More mathematically speaking,
Alpha equals A over R.
exactly, alpha equals A over R.
Bigger R would make it less. Alpha.
Very good. So alpha equals A over R, right? So a bigger R, for a given acceleration, a bigger R gives you a smaller alpha. Conversely, a smaller R gives you a bigger alpha. So the smaller will have a bigger angular acceleration. So, okay, that covers the rest of the material. We'll have a quiz, I guess, Wednesday. I'll post the practice quiz, and we can look at it tomorrow and shore up anything on the problem set we're unsure about. Thanks for the 100 bits.